So part 2 of mathematical methods in physics practice final exam, number 3, consider d dx, 1 minus x squared dy dx, close parentheses, plus lambda y equals 0 for the interval -1 is less than x is less than 1. Okay, so part A, show the equation is Strom-Liouville. Part B, identify P of x, Q of x, W of x. Part C, determine eigenvalues. Part D, prove orthogonality. Part D, normalize the first three eigenfunctions. And part F, expand f of x equals x squared in this basis. So SL theory, d dx of this 1 minus x squared y prime, close parentheses, plus lambda y equals 0. So this is an SL form. Parentheses py prime, close parentheses, to the y prime, plus lambda w minus q, parentheses, y, that equals 0. And we identify p of x equals 1 minus x squared, w of x equals 1, q of x equals 0. So this is Legendre. Some people call it Legendre. Some call it Legendre's equation. 1 minus x squared y double prime minus 2x y prime plus lambda y equals 0. Regularity at x equals plus or minus 1 gives polynomial solutions when lambda equals L times the quantity L plus 1, and L equals 0, 1, 2, on and on and on, with eigenfunctions y sub L of x equals p sub L of x. So orthogonality follows from self-adjointness. So we have the integral here from -1 to 1, p sub L of x, p sub m of x equals 0. L cannot equal m. So the norm is going to be here, the integral from -1 to 1, p sub L squared of x dx. Evaluating that, that's going to be 2 over 2L plus 1. And the first three normalized eigenfunctions are going to be, here we have phi naught equals 1 over square root of 2. Phi sub 1, some will call it phi. Phi sub 1 equals square root of 3 over 2 times x. And phi sub 2, square root of 5 over 8 times the quantity 3x squared minus 1. Some call those phi, some call those phi, depends on whoever's pronouncing. Since p sub 2 of x equals 1/2 quantity 3x squared minus 1, 3x squared is going to equal 2, p sub 2 plus 1. So we're going to wind up with our x squared here is going to equal 1/3 p naught of x plus 2/3 p sub 2 of x. So that's number 3. Moving on now to number 4. So number 4, solve using Green's theorem. We have this second derivative of y with respect to x equals we have the second derivative of y with respect to x minus 4y equals e to the negative x, subject to y of 0 equals 0, y of 1 equals 0. Part A, construct the Green's function from homogeneous solutions. Part B, prove continuity conditions. Part C, derive the jump discontinuity in the derivative. Part D, evaluate the convolution integral. And Part E, verify by direct substitution. So this is a Green's function method problem. We could solve this differential equation. Y double prime minus 4y equals e to the negative x, where y of 0 is going to equal y of 1 is going to equal 0. So the homogeneous equation is y double prime minus 4y equals 0. And solving that, our solutions are going to be e to the 2x, e to the negative 2x. So if we choose two boundary adapted solutions, u sub L of x equals hyperbolic sine of 2x. U sub R of x equals hyperbolic sine of 2 times the quantity 1 minus x. So if we go ahead and calculate here, the Wronskian is going to be w equals u sub L, u sub R prime, and minus u sub L prime, u sub R. So if we evaluate at x equals 0, u sub L of 0 equals 0, u sub L prime of 0 equals 2, and then u sub R of 0 equals hyperbolic sine 2. So W equals 0 minus 2 hyperbolic sine 2, and that equals negative 2 hyperbolic sine 2. So for here, the Green's function for L equals d squared over, for L equals the second derivative with respect to x. That's going to be this g of x comma psi, and that's going to equal this piecewise. For the first component here, where x is less than psi, that would be u sub L of x, u sub R of psi over W. And the second component here for domain where here is x is greater than psi, u sub L of psi, u sub R of psi over W. So we're going to wind up with g of this x comma psi equals negative 1 over 2 hyperbolic sine. And then we have this piecewise sine, hyperbolic sine 2x, hyperbolic sine 2 times quantity 1 minus psi, where x is less than psi. And the second part, hyperbolic sine 2 psi, hyperbolic sine of 2 times the quantity 1 minus x, where x is greater than psi. Okay, so building on that, the solution is y of x equals this integral from 0 to 1, g of x comma psi, e to the negative psi d psi. Okay, so a simpler equivalent direct solution is y sub p equals c e to the negative x. And some people pronounce psi differently. From here, y sub p double prime minus 4 y sub p, that equals c e to the negative x minus 4 c e to the negative x. That equals negative 3 c e to the negative x. Choosing c equals negative 1/3. So we're going to get y equals c sub 1 e to the 2x plus c sub 2 e to the 2x minus 1/3 e to the x. Our boundary conditions here are going to be c sub 1 plus c sub 2 minus 1/3 equals 0. C sub 1 e squared plus c sub 2 e to the negative 2 minus 1/3 e to the negative 1 equals 0. Y of x equals c sub 1 e to the 2x plus c sub 2 e to the negative 2x minus 1/3 e to the negative x. Where c sub 1 equals e to the negative 1 minus e to the negative 2 over 3 times the quantity e to the 2, e to the second minus e to the negative 2. So c sub 2 equals 1/3 minus c sub 1, and this satisfies both boundary conditions and the differential equation. This is part 2. Thank you very much and have a great day.